Welcome back to Advanced Machine Learning. I'm Ludwig Botemann, and in this video I will talk to you about performance measures, especially for imbalanced learning. In the end, you should know some performance measures beyond accuracy, since you already know that accuracy is not really perfect for imbalanced data. You should know the advantages of these performance measures over accuracy for imbalanced data, and you should know some extensions of these measures for multi-class settings. First, let's recap some performance measures for binary classification. We encourage you to first go through the respective chapters of the Introduction to Machine Learning. That's chapter 4.8, for example, but feel free to skim through the other slides as well. So in binary classification, at least if we define the two classes as negative and positive class, so -1 and +1, we can always look at these confusion matrices. In the rows, we have the predicted or classified class. In the columns, we have the true class. And then we can note all the absolute values of true positives, false negatives. And true negatives, those sum up to n, so to the amount of data we have. And then we can compute different performance measures, such as the precision or positive predictive value, which looks at the first row of this confusion matrix and asks how many of those which were predicted as positive are actually positive. In the other direction, there is the recall. This goes column-wise and asks how many of those observations that are in the true positive class are actually detected by the classifier. So dividing TP plus Fn. Okay, and then we have a measure called F1 score that balances the recall and the precision by a harmonic mean. That's 2 times the product divided by the sum of recall and precision. If you have a close look at the formula, you will see that precision looks at TP and FP, recall looks at TP and Fn, which means that the F1 score does not at all have a look at the true negative values here. Okay, so just at the 3 other values. And now, of course, in this chapter we ask ourselves, does the F1 score suffer from data imbalance just like the accuracy did? Or does it not suffer from such problems? Let's have a closer look into the F1 score. The F1 score is the harmonic mean of positive predictive value and true positive rate, so precision and recall. And the property of each harmonic mean is that it tends more towards the lower of the 2 combined values. What does this mean? So if we take 2 random numbers here from PPV and TPR, let's say 0.8 and 0.4, then the F1 score here is 0.53, so somewhat below the mean of the 2 values. The arithmetic mean would be 0.6. We have 0.53 for the F1 score, so a little bit lower than the arithmetic mean of the 2 values. Well, it's just a property of the F1 score. If we have a model with TPR equals 0 or with PPV equals 0, then the F1 score is also exactly 0. Now, what happens if we perform some very non-informative classification? So, for example, always predicting negative. What happens then? If we always predict negative, then the true positive rate, of course, will be 0 because we do not have any true positives. So, harmonic mean of 0 and anything else is still 0. So, F1 score will be 0. Which is good, because we want, of course, have a score which has low values for a rather stupid classifier here. So what about always predicting positive? always predicting positive leads to the following thing. The true positive rate will be 1, of course, because we have no false positives there. And then this harmonic mean of precision and recall will be 2 times precision divided by precision plus 1. And perhaps as a small homework for you, you can figure out why this is the same as 2 times n plus divided by n plus n. And keep in mind that we only have true positives, so f and false negatives are 0. Okay, but let's go back to the important point here. So if you always predict positive, then TPR will always be small if n plus is small. So if you have a very unbalanced data set, then F1 score with always predicting positive is also very small. Okay, so always predicting negative and always predicting positive both leads to a very small F1 score, which is good, of course. So we can finish the slide here with stating that F1 score is more robust to data imbalance than the accuracy is. Well, more about the F1 score. The F1 score puts equal weights to precision and recall, or to the inverses of precision and recall. There is a different score called F beta, which has some beta squared weights put to TPR and PPV. So this and that value are not half any longer, but beta squared divided by 1 plus beta squared, which is exactly 1/2 f beta is 1, of course. But this f beta allows you to put different weights on the precision and on the recall. So if you use a very high weight beta, then the f beta score is more or less the same thing as the true positive rate, so as the recall. And on the other hand, if you put a very small weight beta here in that formula, then the f beta score is more or less the same as the precision. Let's go from the harmonic mean to a geometric mean. Geometric mean is, of course, the square root of the product of 2 things, or well, if you only have 2 things, let's keep it simple here. Then we have 2 different scores we can use. These are the G-score and the G-mean. Both are geometric means of some quantities. So let's have a closer look here. Both use the true positive rate, so the recall, and then the G-score additionally uses the positive predicted value, so the precision, and the G-mean uses the true negative rate. Okay. So as was true for the harmonic mean, the geometric mean also tends more towards the lower of the 2 combined values. Same example here. 0.4 and 0.8 do not result in 0.6, but in 0.57 in that case. If you compare the tables of G-score here and F1 score slide before, then you will see that the geometric mean is larger than the harmonic mean. And good thing also about the geometric mean, or the geometric mean, so the G-score and the G-mean, is that if you always predict a negative value, then you will end up at 0 as well, which is good in terms of imbalancy, but it's not that clear what happens if you always predict the positive class. So balanced accuracy. Balanced accuracy is just the arithmetic mean of true negative and true positive rate. So a rather simple formula here. It's different from the usual accuracy, because for usual accuracy, or what you do here is you compute, let's say, the one class accuracy of the positive class and of the negative class, and you don't really care about how large these classes are. You just take the average of the 2 values here. So if you think about accuracy, then you're not doing this, but you're giving the larger class a higher weight. If a classifier has a high accuracy on both classes, or if the data set is almost balanced, then the balanced accuracy and the normal accuracy are more or less the same. However, if a classifier always predicts negative for an imbalanced data set, so for a data set where we have far more negative values than positive values, then the normal accuracy will be much larger than the balanced accuracy. Another important measure here is the Matthews correlation coefficient, also called phi coefficient. So let's think about the Pearson correlation coefficient. That's more or less exactly what we're doing here. Correlation is covariance divided by a product of the standard deviations. So we look at those two classes as two binary random variables, and we use the entries of the confusion matrix to estimate the Pearson correlation coefficient, and then we end up with this formula here, which I guess is most important here in the denominator. So Tp times Tn minus Fp times Fn. So this means that the Matthews correlation coefficient is high if we have a lot of true positives and a lot of true negatives, and not so high if the false positives and the false negatives are high in numbers. So this means we look at all the entries of the confusion matrix, Tp, Tn, Fp, and Fn. So this considers everything, not as the F1 score, which did not consider the true negative number. And, well, the MCC can also be -1. As you know, for correlation, it can be between -1 and +1. Here again, the formula. If the MCC is 1, then this means we have nearly zero error, because somehow the Fp and Fn values are 0. So everything is true here in that case, so all the predictions are correct, which means we have a very good classification, or a strong correlation between predicted and true classes. If we have 0 here, then we have basically no correlation, so it's not really that much better than random guessing. And if we are on the other side of the 0, on -1, so that's not that bad as well. So we just have to switch the labels, from the predicted labels, from negative to positive class and from positive to negative class. Then we have a reverse classification and a pretty good model here. Okay, and as you see from the formula, you do not have to define which is the positive class and which is the negative class. So in contrast to the F1 score or precision or recall, for example, so MCC does not depend on which class is the positive one, which has some charm, I would say. Okay, so these were the measures for binary classification. Let's go over to multi-class classification now. Multi-class classification means we have more than two true classes. We have G true classes, and we have also G predicted classes. And with nji, we mean the number of I instances classified as J. So in the rows we have J, in the columns we have I in that case. And this one, n21, means we've predicted a 2 and the true class is 1. Then we can sum up all the values in one column and get the total number of I instances. Okay, so the total number of 2 instances is n12 plus n22 plus n32 and so on until ng2. Okay, and with this we can compute the class specific metrics. So for example, the recall for class I, let's say we are here in, okay, let's clean up a little bit first. Let's say we look at this class here, we want to have the recall of that class, so that's n22 divided by the numbers in the total number in that column, okay, so n22 divided by n2, so the sum of everything here. We can do the same thing for all columns, of course. We can also have a look at true negative rate. And then true negative rate means we kind of binarize the problem. Okay, so we have a positive, so now we have a positive and a negative class again. So the true negative rate for class 2, for example, is summing over all the diagonal elements, but not in that column. So again, for column 2, we sum over, n11 and 3, 3, and so on. We sum those up and divide by what? By the number, the total number of all the observations that are not in the second column. Okay, so n minus ni, so all the numbers which are not in that column too. That's a true negative rate. And then we have the positive predictive value or precision, again, which looks at the columns, at the rows as before. So for example, precision for row j is njj. Let's say we look at this one here and 1, 1 divided by everything in that row here. Okay, and our problem with those multi-class measures always is that we have a lot of those. So we have a true negative rate or a true positive rate for class 1, we have one for class 2, for class 3, then we have all positive predictive values, and it's just a lot. So, but in the end, we like to look at perhaps not just one value, but not at like g times the g values. So we kind of want to average those single values here. And one option is to, perhaps somehow naive, but okay, let's just take the arithmetic mean of some metrics, okay? So let's say, for example, we look at a class-specific positive predictive value, and then we just take the mean of those positive predictive values over all classes. Or do the same thing for the F1 score, for true positive rate, and so on. So one example would be then to use those macro, or these not weighted, these averaged. Okay, once again. So let's say we have computed the PPV and the TPR mean over all those classes, which means we have then a row macro PPV and a row macro TPR, and then we can put this into the F1 score formula and get a macro F1 score from those macro precision and recalls. So, but then of course the problem is that the class sizes are not considered. So what about applying different weights to the class specific metrics? Can of course do that. And here is more or less the same formula than before, but we have a times wi here, so which means we are weighting those metrics. And those weights of course should sum up to 1. And in this case, where we want to put a higher weight to minority classes, we have to make sure that the weight is larger if the class is smaller. Okay, that's a decision that we make, but in case of imbalance, we can decide to do this. For example, we can do something like this here. Then again, we can compute a weighted macro F1 score, which just uses the weighted macro precision and the weighted macro recall here. Of course, same thing applies to G-score or weighted balanced accuracy. So usually you could also use as weights ni divided by n, but then of course for an imbalanced data set you would overweight the majority classes. So that's a design decision that you have to make. Do you want to weight the larger classes higher, or do you want to weight the smaller classes higher? Okay, some last performance measures here for a multi-class case. We also have micro versions. So for example, the micro true positive rate is the sum of true positives over all the classes divided by the sum of true positives and false negatives over all the classes. And the Matthews correlation coefficient can be extended to this rather larger formula here, where ni hat is the total number of instances classified as I. Then we have Cohen's kappa or cross entropy that also treat predicted and true classes as two discrete random variables. So in the end, now you know a lot of measures, but which measure will you use in practice? That's a good question, and there's no good answer to that question, so at least no general answer. So these different measures focus on different characteristics. So depending on your application and the importance of those characteristics in your application, you have to choose for which measure you go. so it's nothing you can just plug and play, let's say, but well, you have for each application to think about what are you trying to reach and which measure helps you reaching that goal the best. At least it should be clear that accuracy is not the way to go for imbalanced data sets, and you should use alternative metrics. And one last word of warning: be careful with comparing the absolute values of the different measures, as these can be on different scales. So for example, Matthew's correlation coefficient and balanced accuracy don't have the same scale. Okay, Matthew's correlation coefficient was between -1 and 1, and Buck is between 0 and 1.